I want to finish up Ampere's law today, the last part of chapter 22, and then hopefully we'll have time to start the next chapter. We introduced last time Ampere's law as the path integral B dot dl over a closed loop being equal to mu naught times the enclosed conventional current. So it's another equation like Gauss's law where we're looking at the pattern of field and talking about something inside some geometrical arrangement. Okay, only it's not a closed surface now; it's just a path. And if you find a non-zero contribution to this thing, then it's telling you there's some current that's passing through that path. It's sort of piercing the surface that's bounded by that path. Okay, so for example, if you have some circular loop or any shape loop, really, much like Gauss's law, the shape doesn't matter. It's just whether or not we get a positive or negative contribution to this thing. And so if you end up, well, let's just look at this example we saw last time where you had magnetic field in a circular pattern. And so if you chose a path integral that goes around in the same pattern, this circular pattern, that's delta L and that's B, then you get, when you add it up round trip, you get a positive contribution. And so that's telling you that there is a current passing through the center, or not even necessarily through the center, just somewhere in this loop. But for this symmetric arrangement, it was the center. And so that was conventional current coming out towards us. There's a directional issue here, and which we didn't mention last time, which is this. If you choose a path that's counterclockwise, for example, and the path integral is something that the direction you can choose yourself. If you choose a direction that's counterclockwise and you get a positive number, what's that telling you about the direction of the conventional current? Well, it's actually another right-hand rule to govern the directionality here. You go around in the counterclockwise direction. If you choose your right hand and your fingers curl around in the direction that you're traversing this path, then your thumb gives you the positive direction. Okay? So in this case, if I go around and I get a positive value, that's telling me that there's conventional current coming out in the positive direction. Okay? Had I chosen the same, if I had the same magnetic field, so that's B again, but I choose a path integral in the opposite direction, so delta L is that way, then when I sum up all those dot products of B and delta L, now I'm going to get a negative number, right? But the direction of the current should be the same. So how do I make sense of this? Well, in this case, I get a negative number over here. So this side's negative, which means the answer I'm going to get for the current is going to be less than 0. So mu is going to, the current's going to give me a negative value. But that tells me the positive value, since I'm curling my fingers around of my right hand and around in the direction I'm going around in this path, the positive value is into the board. So the negative value must be out of the board, and so we still get the same direction for the current. Okay, so just be careful of the sign. The sign here is the direction. The positive direction is given by your thumb when you go around, when your fingers curl around in the direction of the path. Okay. So we were looking at this problem last time, and I just want to finish up with this. So let's take a look at this problem again. Okay, we were looking at this rectangular path. And this is some pattern of magnetic field, okay? And we're just measuring the magnetic field at various points along this rectangular path. So once again, this isn't a box. It's just a flat. It's really, we're looking at the edge of a flat surface, okay? And so here's our path. And I'm going to pick, again, a counterclockwise direction for my round trip integral here. And we talked last time about how you'd have to break this up into each individual segment. We have B2 pointing that way. And on the other side, B2 pointing that way. And on the top, we have B1 making an angle theta with our path, and then on the bottom, B1 is in the opposite direction, but it still makes an angle theta with the path. And let's see, the width is 0.5 meters, and the height was 0.2 meters. Okay. So you go round trip, have to start somewhere, so we start, say, over here, and we're going along this path upward, and everywhere along this path, the path length vector, delta L, is perpendicular to the magnetic field. So along that segment, B dot dl is going to be 0. Okay. So we have, so if I'm thinking about summing up all the B dot delta L's, then just call it 1, 2, 3, and 4, just to label them here. Along 1, we get a contribution of 0. And then along 3, we're also going to get a contribution of 0, right? So only segment 2 and 4, we're going to get a non-zero B dot dl. So let's try it. See if you can calculate B1 dot delta L and B2 dot or B1 dot delta L on the top, B1 dot delta L on the bottom. Remember the path, if we're choosing, we're going around counterclockwise. So on the top, your path vector is going in the negative x direction. On the bottom, your path vector is going in the positive x direction. You should be able to use that and find what the total round trip B dot dl is going to be for this path. So let's try this out. Okay, so biggest vote for answer 3, which is 1.7 times 10 to the minus 4, and it's just the units are just Tesla times meters, the magnetic field times the length, and I believe that is correct. You're going to get, and so some people were just having a conversation. Why isn't it 0? Well, because you get a positive contribution at the top, and you get a positive contribution at the bottom, because your delta L vector here is in the negative x direction. So that delta L is going to be negative 0.500 meters. Down here, delta L would be positive 0.500. On the top, you have a negative x component for delta L and a negative x component for B1. On the bottom, you have a positive x component for delta L and a positive x component for B1. So when you do those dot products, you get a positive dot product at the top and a positive dot product at the bottom. So if you can just find the B dot dl at the top, you know it's got to be the same at the bottom because it's the same magnitude of field, same length, and same angle. Okay, so let's just figure that out. We have on segment 2, we have the magnitude of B1 times the magnitude of delta L times the cosine of 30 degrees. So we get 2 times 10 to the minus 4 times 0.5 times cosine 30, which is equal to what? What does that give us? Well, half that, right? So that'd be, what's half of that? 1.7 divided by 2 is what? What was it? 0.85? Okay, so 0.85 times 10 to the minus 4 Tesla meter. And then, as we said, the bottom segment, 4 is going to give you the exact same thing. So in the end, you can finally add them all up and say that the sum of all those B dot delta L's gives us 1.7 times 10 to the minus minus 4 Tesla times meters. And then the final step is we can apply Ampere's law and figure out how much current is running through that rectangular loop. First of all, what's going to be the direction? Is the current coming out or going in to the board? It's coming out, right? Because we went around counterclockwise, we got a positive value, and so that's telling us the positive direction is out, and so if we get a positive value, that's telling us the current's coming out. Now, we don't necessarily know where this current is. It could be here. That could be the current coming out, or it could be here, or it could be spread throughout, or there may be several currents coming out. And in fact, the way this pattern of field is, it looks kind of odd. There might even be sources of magnetic field elsewhere, but that's okay. All we know is that the total enclosed current, when you add it all together, has got to be equal to this divided by mu naught, right? So we get B dot dl divided by mu naught, so that's going to be 1.7 times 10 to the minus 4 Tesla meters over 4 pi times 1 times 10 to the minus 7 Tesla meter per ampere. So we're going to get units of amps. And what's that work out to? Someone calculate it? What do we got? 135? Okay, kind of a large current, but this is just an example. Okay? Questions on any of this? Everybody okay here?